Hello, my name is Zhang Ziyuan from Section 2, Group Wrong Rag, and I will walk through the code. The system is a concurrent periodic test in a pre-compute uh, actuate pipeline modeled on the Micro COS2. Two cameras feed four compute tasks. Decision fusion, marking them and set controls diverse the car. Critical tasks never call each other. They share one dictionary guide by the mutex. All shadowing lives in one class, RT tags. Three ideas, concurrence. Each task is its own trait. Third, period. Each task lives for what's left of its period, so it fires at the fixed rates. Sleep equal period minus runtimes. Third, priority. We use red monotonic. The shortest period task get the highest priority, mapping to 3 OS tiers. Story says we stay safe under about uh, 32 CPU uh, utilization. Third, what runs each cycle? First, say classical OpenCV CLAHI, then HSV cover mask, then control filter, no machine learning, so timing stays predictable. Decide scores 5 lanes to chase green and doggy right and yellow. Plot even modes for darkness, police, chasing car, and the golden line. Third, actor. Decision fusion smokes the readout and send the control send two floors every 5 milliseconds. Honest limits. Python's log has no periodic inheritance, so a median task can block a high one. Classical periodic invention and the Windows sleep timer jitters against the free RTOS benchmark. We have three periodic levels, no 32. And the shorter, not headlines. The payoff, a peak of 21,509 meters, mean 30,000 across 11 rounds, and the variation checks yellow sabotage tokens, not our navigation. Okay, thank you.
Hello everyone, my name is Shomyo and for my part I'll be walking you through the results and findings of our speed trials 2D simulation. We ran the system 11 times under live game conditions, so let's get into what happened. So just to give a quick recap of the environment first, Speed Trials 2D is a Unity-based simulation where our Python control car has 60 seconds to travel as far as possible down a track. Along the way, it picks up tokens. Green ones give a speed boost, red ones slow us down, and yellow ones are the problematic ones. Yellow tokens trigger one of 5 random sabotage effects, things like corrupted camera input, hidden tokens, delete control output. On top of that, the simulation throws in random events like a police car, a chasing vehicle, or a sudden darkness event that blacks out our camera. Our system handles all of this using 8 concurrent tasks running in a perceived compute actuate pipeline, which is modeled on the RTOS principles. Alright, so here are the full results across all 11 trials. You can see the distance, green, red, and yellow token counts, and the net score for each run. The standout run is trial 7, highlighted in green, where we hit 21,509 meters. That is also the run with the lowest yellow token count at just 7, and a combined penalty count of only 18 across red and yellow. Everything worked properly on that round. On the other hand, trial 5 was our worst at 9,879 meters. That run collected 18 yellow tokens, the highest in the entire dataset. And the sustained sabotage effect basically overwhelmed the event handling logic. The car couldn't recover fast enough between the disruptions. What is also interesting is that in trial 8, it's the only run in the entire dataset with a positive net token score of +2, meaning we actually collected more green tokens than red and yellow combined, and it still only came in third. That tells you that yellow sabotage effect it has like more impact on the results than the other tokens actually. Okay, lastly for the stats, our average distance was 13,024 meters, best was 21,509 meters in trial 7, and the worst one was 9,879 meters in trial 5. So basically the results actually come down to the yellow tokens actually. Runs with fewer yellow went further, runs with more yellows went shorter. Trial 7 only had 7 yellows, trial 5 only had 18. So that's why 7 was better, 18 was worse. The car itself was driving fine the whole time. The yellow sabotage effects are the one that were like messed all the results up. So that's all from my part. Thank you.
Hello everyone, my name is Xin Qinghao, and now I will present our case study and physical real-time system proposal. So as you can see, the part 4. Our reference case study is free RTOS-based autonomous vehicle system introduced by Kumar and Lisa in 2025. The system uses a camera, LiDAR, ultrasonic sensors, and an IMU. Each sensor operates as a separate real-time task. Tasks with shorter period receive higher priorities. The system also measures the worst case execution time, or WCET, on real hardware. So you can see the table. We compare two systems. Our speed trail 2D system has a similar structure. Both systems use separate tasks for perception, decision making, and control. However, there are some important differences. Our system uses Python set on Windows and has only one priority levels text share information through uh, dictionaries and logs. Python logs do not support priority inheritance. Therefore, highly priority tasks may need to wait for lower priority tasks. This problem is called priority inversion. In comparison, free RTOS provide more priority levels, priority inheritance, message queues, and formal WCET testing. Therefore, it's more suitable for real vehicle. So, uh, you can see the part 5. Based on comparison, our proposal several improvements. First is decision functions and send controls should be used private data area and a separate log. This can reduce waiting time. Second, this important tasks should run on a dedicated CPU core. We also reduce the decision functions period for 5 milliseconds to 2 milliseconds. This would improve the response speed at a high vehicle speed. So you can see the sensor and the structure scaling. Third, the physical system should add a LiDAR radar and an IMU. A sensor fusion task would combine all sensor data into one environment model. Double buffering should also be used. One task can write new sensor data, while another task reads the previous data. This reduces log waiting and improve performance. Finally, the system must be tested on real hardware. We should measure WCET over at least 10,000 tasks executions. We should also have hardware in the log testing. A real controller runs the control software while speed trail 2D simulates the warehouse. This allows us to test timing and safety without using a real car. So, in conclusion, our simulation has suitable based decision. However, a physical vehicle need better coding, safer combination, sensor fusion, and hardware testing. Thank you.